isInfiniteProcess, number 12. Okay, so basically this is kind of an interesting problem because in some ways it's a little bit meta. They're asking us about this program right here. You know, they're saying if we were given two integers, so two whole numbers, A and B, we want to know, is this thing, so this is pseudocode, it's not written in any particular language, it's language independent. But anyway, the idea is that it's saying we've got A and B, and while they're not equal, we want to increase A and decrease B. Okay, so like an A plus plus, a B minus minus basically. And we want to tell, is this going to go on forever or no? Because the only situation under which this would stop, the only thing that would like terminate this loop, is if A ended up being equal to B. So as long as they're not equal, it's going to go on forever, right? So that's really what we're trying to check. Is this going to be an infinite loop or not? Okay, so let's give it a try. I mean, I think the simplest way to try to figure this one out would be to actually run it, you know, to actually try it. So we'll say while A is not equal to B, and we'll say A plus plus, B minus minus. Okay, and then if it makes it past that, if it's not, like if this does terminate at some point, we'll say return false, because that must mean it's not an infinite process. It didn't go on forever. Okay, cool. So let's give that a run. We'll see what happens with this one. And, you know, now that I'm thinking about it, there's another way we can modify this. We could probably put like the A plus plus and the B minus minus in here. But okay, here we go. So the first one, false, so that returned what we were looking for. But this next one, it didn't return anything because it timed out. It was an infinite process, so it should return true. And in that sense, it's properly identifying it. I mean, it's doing what we want it to do. But the problem is that it's hard to tell if it's giving us this infinite process, because if it does, it's just going to time out. And it's not going to be able to get to the rest of the tests because it only has 4,000 milliseconds. Okay, so maybe there's a way we could sort of time that, you know, to try to tell if it's taking that long or not. And yeah, let's basically do that. So we want to time this thing. We need some way of like telling how long it's been. Now, originally I was thinking we could use like a set timeout, which is pretty common in a browser environment, but I couldn't get it working in here. I don't know if it's because it's like a node environment or what it is, but anyway, I couldn't get set timeout working. So instead what we're going to do is we're going to use Date.now. So let's talk about that for a sec. If we were to just return Date.now, we'd get a number, and it's a really large number. In case it's not obvious what this number represents, let's do a little bit of work here. So first of all, one little spoiler I'll give you is that this represents a number of milliseconds. Okay, this is milliseconds. So let's divide by 1,000. So now it's going to be seconds. Okay, and let's say we don't just want the seconds. Let's say we want the minutes. So we'll divide by 60. And maybe we actually want the hours. So we'll divide by 60 again. And maybe the hours isn't good enough. Let's get the number of days. We'll divide by 24. And let's get approximately the number of years by dividing by 365. Maybe like 365.24. I think that's a little more accurate. But anyway, let's run this. And you notice it's like 47.9 years. Okay, so we basically converted this thing to years. It's been about 47.9 of them, so almost 48. Folks, Date.now represents the number of milliseconds that have passed since the beginning of time, which, as you may know, was January 1st, 1970. Okay, so basically that's what Date.now is giving us. It's the number of milliseconds that have passed since January 1st, 1970. At midnight, I think. Anyway, the point is 47 because we're in 2017. The 0.89 is because we're, you know, pretty close to the end of the year. It's almost December. So basically that's the idea. Now, you might be thinking, how would it be useful here to know how many milliseconds have passed since January 1st, 1970? Maybe it doesn't seem all that useful. So here's what we're going to do. We're going to say start time is assigned the value of Date.now. And then basically, when we're running our loop here, actually, before we get into the loop there, let's just do something like this. Let's say, just run a little quick little for loop. Okay, so something that's going to go from 0 to 1,000,000 one at a time, and it's basically just going to do nothing. And then after that, we're going to return, we'll say date.now minus start time. Okay, so we'll run that, and we find it's giving us 5. That one was just a 1. This one, 0. Wow, okay, so some of these are fast. Let's try running it again. We'll see if we get the same numbers. No, this time we get 4. Okay, so let's make this a bit bigger. Let's say instead of going from 0 to 1,000,000, maybe it's 10 million now. Okay, so this is actually starting to take some time. 25 milliseconds for the first one, 15 milliseconds for the second one, 12 milliseconds. It goes through these pretty fast, eh? Let's see if we want to go from 0 to 1,000,000,000, how long that's going to take. A billion's a lot bigger than 1,000,000. So yeah, okay, it didn't even finish in time. This one took 970, 744. So it's taking a lot, you know? Like, these are close to a second each time. It's close to 1,000 milliseconds. It's close to a second. So this takes almost a second. This takes like 3/4 of a second, 3/4 of a second, 3/4 of a second. By the time we get to this one, we don't have enough time left because we only have 4 seconds to get this all done. But anyway, the main thing is that what we're finding is that we're getting these numbers. We're able to tell, according to this Date.now, if we do a subtraction, so if we take the current moment, the current number of milliseconds that have passed since January 1st, 1970, and we subtract from that the number of milliseconds that had passed since January 1st, 1970 when we first started the program, that'll give us a difference. It'll give us the difference in milliseconds between the start time and the current time after running this loop. Or I guess really what we want to do is, in this case down here, we want to get the current time when we're running each of these, you know? So we're going to do our A++, we'll do our B-, and we'll say if date.now minus start time is greater than 4,000, then return true, because it is an infinite process in that case. So let's try that. And something we're going to notice is that we're being a little bit greedy here because we're saying if it's greater than 4,000. Well, keep in mind, it's already checking to see if it's greater than 4,000, or in other words, 4 seconds. It's already checking that, and it's going to naturally time out if it does. We can't afford to let it go that long on each of the tests because it needs to get through all of them in 4,000 milliseconds, and we've got 20 tests. So let's make it 4,000 divided by 20. So that'd be 200. So let's say if it's greater than 200, if it's greater than 0.2 seconds that it's taking, just return true. So let's try that. And okay, cool. Looks like it's working. We're getting the answers we're looking for. Let's see if that's going to pass the hiddens. And yeah, it does. Okay, cool. Oh, that's great. Okay, let's close this up. And I want to make one modification. This just occurred to me when we were looking at it before, but can we do something like this? It'd be kind of neat, right? No, we can't. I wonder why that is. Is it because we're not doing these modifications? Oh, it's because we're supposed to increase A. Whoops. plus A minus B. Let's see, does that work? Most of them. Oh, right. It should have been actually the other way because we wanted to compare these things first and then change the values after that. Yeah, that's what we want, I think. Yeah, okay, cool. Well, that's pretty neat. That's getting a little more efficient. I mean, we could even, since it's just one line, we could sort of get rid of these braces here and move this up there. And yeah, now it's looking pretty tight, pretty not bad. Is there any other modification we want to make here? Let's see. I mean, this seems like it's running fine. If you think about it, one thing I'll mention is there are really, I guess, 2 cases where this might go on infinitely. They sort of boil down to the same case, but basically the main thing is if we find that that A is already bigger than B, then they're just not going to be equal. They're getting further from each other at that point because A, it's already bigger than B, and it's getting bigger, and B is getting smaller. We're not going to get to a point where the 2 are equal. So that's basically the situation here. Now, what we could do just for the ones where it's meant to return true, let's return A actually. I want to see how big it's actually getting. Are we giving it enough time to grow and to thrive? Well, that was a false. Yeah, okay, so A starts as 2, and it's getting all the way to about 2 million. I'd say we're letting it run long enough. So I'm satisfied with that. I think that's a good little algorithm. I think it's neat the way we're basically looking at this in sort of a brute force way. We're pretty much just following exactly what they ask over here. So this is like really, really taking the problem literally, which I like to do sometimes, as you may notice. Okay, so cool. That's good. I like that one. But there's another way we can look at it. I mean, we basically just said a second ago that what this depends on is if A is already bigger than B. If A turns out to be bigger than B, then we're going to have an infinite process. So let's return A is bigger than B. Let's see if that works. Well, actually, for 7 out of 10 cases, yeah, we're right. But I'm curious about the ones where we're not right. So in this case, yeah, A is less than B, but it still says we're failing here. It still says, we're getting false here, but we should be returning true. This should actually be an infinite process, even though A is less than B. So why is that? Well, basically A starts as 2, B starts as 3. They're going to miss each other. A is going to get incremented up to 3, B is going to get de-incremented to 2. They're going to pass each other like ships in the night. They're never actually going to become equal, but they will pass each other's values. So that's kind of an interesting situation. We need to take that into account. So either A is already bigger than B, or what we could say is that they'll miss each other. So when will they miss each other? Well, notice part of the issue here is that every time we increment and de-increment, so A goes up by 1, B goes down by 1, the difference between them shrinks by 2. Okay, so like in this case, there's a difference of 1 between them. After we increment A and de-increment B, there'll be a difference of -1, or an absolute difference of 1. The point is, it never gets exactly down to 0. Whereas if we have a case like this where A is 2, B is 6, the difference between them is 4. We increment, the difference will be 2. Increment again, the difference will be 0. And that's really the situation we're looking for. So what we need to make sure of, in order to actually get down to 0, we need for the initial difference between these two numbers to be even. Because if it's not, like, we're subtracting 2 each time. It's either always going to be even or always going to be odd. So we need for it to always be even, because otherwise we're never actually going to reach the difference of 0. So notice this case where it was failing, there's an odd difference between them. If we look at this other one, there's an odd difference between them. There's a difference of 5. So they'll miss each other again. The difference starts as 5, then it'll go down to 3, then down to 1, then down to -1. We miss each other. We don't actually go through the 0. So we need that 0. We need to make sure that the difference between them, B minus A, and keep in mind, okay. B minus A, I'm saying, is the difference between them. And you might be looking at that and thinking, but doesn't that mean that could maybe be negative? Don't you need to check if that's like a positive number? And I don't, because if it's going to get to here, that means this must not have been true. If this was true, it wouldn't bother checking the next part. It already knows enough information. This or this, yeah, this one's true, so the whole thing's true. So the only time we're actually going to get to here is if this is false, if A is not greater than B. So in other words, B would have to be greater than or equal to A. So we know that B is going to be the bigger value, so B minus A should give us a non-negative value. And what we're trying to say is that if we take mod 2, we get something odd, right? We'd get an odd number if we were to try to divide, an odd remainder if we were to try to divide this difference by 2. That's the idea. So we're saying, well, it'll be infinite. It'll be an infinite process, either if A is bigger already, like right from the beginning. If A is already bigger, they're just going to widen the chasm between these two numbers. And if it's not, then we need to check that there's an even difference between the two. Because if it's an odd difference, they'll miss each other, and it'll also be infinite. So this is if there's an odd difference. This is if A is greater. Okay, let's see if that's enough. Okay, great, it is. Now, one more thing I want to say is that you may recall 1 is going to get typecast to true anyway. So I actually don't even need that part. It's kind of like saying something is equal to true. We don't need to check that. If it's true, it's true. So not bad. Not bad. I mean, I thought this was pretty efficient, but I think this is even better. So basically, the main difference is that we're sort of zooming in on the conditions that'll produce an infinite process here, as opposed to the other one where we're actually trying to simulate the infinite process and make it happen. So some differences in terms of how we go about it. Now, which is going to be more efficient? Well, this one by like 1 billion. Like, this one, we're letting it run. We're letting it take up the amount of time that it sort of needs to tell if it's going to go on forever. So, yeah, whereas this one is just direct. We feed in the numbers, boom, big O of 1, no problem. Okay, so, and this is getting kind of like nitpicky, it's getting very technical, but in a sense, we could say that this one is running in constant time simply because if it gets to be over 200 milliseconds, it'll cut it off. But, not all constant time algorithms are equal. The idea is that whether or not they have the same complexity, this one is still going to take a much longer time. So that's the main thing. Anyway, we got it done. I think it's going to pass all the hiddens. Let's just make sure. And yeah, there we go. Okay, so we'll finish up that one for now. Yeah, nice job. You did it. Okay, we'll take a look.